Today we'll talk about another important law which sort of mirrors the previous law that we discussed, which is the Biot-Savart Law. The Biot-Savart Law, if you recall, allowed us to define the magnetic field at a distance r, small r, from a current carrying element. So it was one way of defining what would be the strength of a magnetic field at a distance r at a point P due to a current carrying element dl carrying a current of I amperes. So the Biot-Savart Law stated that the magnetic field is directly proportional to the product of the current carrying element with the distance vector, so which is vectorially represented and inversely proportional to the square of the distance. So we represent it as r cube because eventually the r in the numerator cancels out one of the r's in the denominator and it's inversely proportional to the square of the distance. So this is basically what Biot-Savart Law stated. Now Amperes Circuital Law is yet another method to measure the strength of a magnetic field at a distance p from a current carrying conductor or a current carrying element. So what does Amperes law state and how does it differ from the Biot-Savart law? Amperes law basically approaches the problem from a slightly different perspective. So let's try to find out what Amperes Circuital Law is all about. So let's assume that there's a current carrying conductor carrying current I, and I define a current element dl. Now if I define a point P of interest where I need to find out what the strength of my magnetic field is due to this current carrying conductor, or in particular this current carrying element is, then Amperes law starts by asking you to consider the whole problem by assuming a loop, an invisible loop of radius r, which is the distance between the current carrying element and the point of interest P. So once you define this loop, now Amperes law states that if dB is the magnetic field due to this current carrying element dl, and if I take the integral and more specifically the line integral, so we call it the line integral. It's a concept that you'll come across much later. There's a difference between line integral and the normal integral. The normal integral is what is taken over the entire surface. So for example, if you go back to our discussions of the Gauss law, in the Gauss law we wanted to find out what the electrical flux is due to a charge or a point charge inside a conductor or inside an enclosed space. In which case we found out what the field or the flux is at one point on the surface due to this charge, enclosed charge, and then we took the integral for the entire surface area. A line integral is a slightly different concept. In a line integral, we take the integral only along the length. We don't consider the area, rather we only consider the length of the electrical electricity conductor over here. So which means when I am taking a line integral over here, I am considering other subsequent current elements along the length of this current carrying conductor. So if I take the line integral of the magnetic field as a vectorial product with the current element, then Amperes law states that this integral is equal to mu naught times the current which is enclosed within this imaginary loop that I have considered. So what is the current that's enclosed within the loop here? The only current that is flowing within this loop is the current I. So which is why it is mu naught times I. Now why is this defined so? To consider that, let's consider yet another scenario. So Amperes Circuital Law, if I were to give it to you in the form of a statement, it basically states, as defined earlier, the line integral of all the magnetic fields due to each of the individual current elements is equal to mu naught times the total enclosed current. So what is the significance of this I enclosed? To define that a little more clearly, let's take this scenario. Let's say there is a current carrying conductor which is carrying a current I1. There is yet another conductor which is carrying a current I2 in the opposite direction. And there is a third conductor that's carrying another current, let's say I3. And there's one more current carrying conductor, I4, and there's yet one more carrying current I5. Now suppose my point of interest is P and it lies here, and I define a loop taking this as the central conductor at a distance R, and my loop goes this way. Now, whenever I consider the magnetic field dB at this point, this magnetic field is the sum total or the algebraic sum of the magnetic fields due to the currents I1, I2, I3, I4 and I5. So be very clear, the magnetic field at point P dB is the total magnetic field being generated as a result of the algebraic sum or the superposition of the magnetic fields due to I1, I2, I3, I4 and I5. But Amperes Circuital Law states that if you take the integral, line integral of all the magnetic fields due to all the current elements, so the different current elements would be DL here, there would be one more DL, again there will be current elements over here, again current elements at this point, again current elements on this conductor, and finally current elements on this conductor. So if you take the line integral of all the current elements, this is equal to mu naught times I enclosed. Now let's try to find out how is I enclosed defined over here. I enclosed means it is the algebraic sum of all the currents within this imaginary loop that we have assumed. So what are the currents that are flowing within this imaginary loop? It's I1, I2 and I3. So this now translates to mu naught into, let's say, the direction of I1. I take the direction of I1 as upwards, direction of I2 as downwards, and direction of I3 upwards. So if I take I1 to be positive, it's I1 minus I2 plus I2. Why only 3 currents? Why am I not considering I4 and I5? Because I am interested in only I enclosed. Whatever currents are enclosed within my imaginary loop, that's what I am interested in. So if you look carefully, the magnetic field that is being developed at point P is due to all the currents. But if you take the line integral, Amperes law states that it is mu naught times, or the permittivity of free space times the currents enclosed within this space and not the ones outside it. So if you just stop and recall that you have heard something very similar when we talked about the Gauss law too. Even the Gauss law, if you recall, the flux on any closed surface is due to the charges enclosed within the closed space and not due to the charges outside. Same way over here, the total magnetic field at this point, though it is the net result of all the current elements, Amperes law states that it's equal to mu naught times of the current enclosed within the imaginary space we have created for ourselves. So this is how Amperes circuital law closely resembles the Gauss law. Now to take the discussion further, before we proceed, this loop, this imaginary loop, we'll henceforth call it the Amperian loop. Now suppose I am looking at this whole arrangement from the top, perpendicular to the direction of the current carrying conductors. Then I will be able to redraw this diagram as this being my loop, and there is I1 which is coming out, there is I2 which is going in, I3 which is coming out, I4 which is coming out, and I5 which is going in. So this is my Amperian loop. So what have I done? I have considered the possibility that I am looking at this entire arrangement of 5 current carrying conductors and my Amperian loop. I am looking at it from the top. So I will see something like this. So this sign convention, if you recall, is current coming out of the board, and this sign convention means the current is going into the board. So I1 is coming out, I3 is coming out, I4 is coming out, I2 and I5 are currents that are going in or going downwards here, right? So they are going into the board now, since I am looking at it from the top. Now Amperian loop is an imaginary concept. So Amperes circuital law, when we apply it to everyday life, we make some basic assumptions that allow us to easily apply this law to different kinds of current carrying loops that we encounter in everyday life. So if you look at this schematic over here, now the magnetic field, one assumption that we can make is that the magnetic field at this point P is always tangential to the loop. So if it's this point that I take, it's tangential, it's going in this direction, right? So the net magnetic field at this point, which is what we consider B due to all the current carrying conductors in its vicinity, is going in this direction. If I consider a point P here, I again assume that the magnetic field is tangential to the loop here. If I consider a point here, then I again assume that the net magnetic field is tangential to the loop at that point. Or if I assume a point here, again the magnetic field is tangential at this point. Now when the magnetic field is tangential to the loop, then the angle that the current element makes with this particular point, right, the imaginary current element that is producing the net magnetic field makes with this point will always be 90 degrees. In which case, if I take this expression, the line integral, the left hand side, this now b gets resolved and comes out, and inside the integral you have dl with sine theta. So now sine theta, theta becomes 90, so sine theta resolves itself to 1. So what you are left with is b across the line integral of dl, of all the line elements, right? So this is how it reduces itself when we make the first assumption. Our assumption 1 is that the magnetic field B is tangential to the loop. My second assumption is, suppose B is normal to the loop, which means the loop is in this plane. Assume that the loop is at this plane. Then the magnetic field is normal to the loop. It is not tangential. Tangential was in the same plane, but it was tangential to whichever point I considered. But now normal is it is either going in the upward direction or it's going in the downward direction to the plane of the loop. In which case, now my theta reduces to 0. So my sine theta or sine 0 reduces to 0. So this entire term tends to 0. So it becomes 0. So the net magnetic field in the second assumption is when B is normal to the loop. The third assumption that we consider is B itself vanishes. So when does B vanish? So when the net algebraic sum of all the current elements, or the net current is 0, or if it's a single current carrying element, then when the current reduces to 0, obviously the magnetic field too disappears. So with these three assumptions, we can then start applying Amperes Circuital Law to everyday conditions. Suppose we consider an infinitely long current carrying conductor, and I want to apply the Amperes Circuital Law, and I assume a circular loop as the boundary, and I want to find out the magnetic field at point P due to the current carrying conductor I. Now as per Amperes Circuital Law, we take the integral multiple and we know it's equal to mu naught into I. Now if I take the left hand side, instead of an infinite length, if I consider a finite length of length L, then the integration of line integral of all the current elements within that reduces to dl. Then my equation as per Amperes Circuital Law reduces to this one, which means B is equal to mu naught I by L. So the three assumptions will now allow us to apply Ampere's Circuital law to any kind of loop. So in all this discussion so far, I was always assuming a circular loop, but that may not be true. So if I have a current carrying conductor which is carrying current and emerging out of the board, I need not always assume a circular loop. I can also assume any random shape. The reason I assume a circular shape is for the simple reason that it allows me to easily calculate the boundary length. Now, suppose I assume a circular shape. Then my integral, line integral of all the current elements has to be divided into two components. The integral of all components where B is tangential to the loop plus integral of all line elements where B is normal to the loop. So let's say for half the circle B is tangential. So if I choose any point here, it's tangential. Any point here, or any point here, or any point here, it's all tangential. If I have a circle here, for half the circle, for a semicircle, the B value is always tangential to this semicircle. In which case, this integration becomes B into the first part becomes the entire length of the circle is 2 pi r, the circumference, half of it is pi r. Plus, so in the case of the B being tangential to the loop, we already discussed sine theta becomes sine 90, which is 1. So I am left with the term pi r. Whereas pi dl, where B is normal to the loop, sine theta becomes sine 0, which is 0, and that reduces to 0. So I am left with B pi r. So B pi r becomes the left hand side of the equation. So B pi r becomes equal to mu naught times I, which is the current flowing through the conductor at the center. So the rest of the semicircle, so this half, which is corresponding to this part, it is normal, which means B is either going in or coming out. So if this is my second half of the circle, then B is normal to the boundary of the semicircle. So this is how Ampere's Circuital law has to be applied. So suppose it were tangential all across the circular loop, then the entire line integral will reduce to, the left hand side will reduce to B into 2 pi r equals mu naught I. So you can keep B on one side and your equation reduces to mu naught I by 2 pi r. Suppose it's an infinitely long electric conductor, and let's say for you're considering a boundary loop, and for let's say this length of the loop, it is all tangential. The B value is tangential at any of these points. So for this length, then integration of B dl will now translate to B into integration of all line elements dl, where B is tangential to the loop. Then that becomes L. So if the length of such line elements all across, so if it's here it's tangential, here it's tangential, here it's tangential, here it's tangential, and in all other places it is normal. Say here it's normal, here it's normal, here it's normal, here it's normal, here it's normal. But at these dark places, the darkened places, it's tangential. And the total length of these line elements adds up to capital L. Then the left hand side becomes BL equal to mu naught I. So this is how you need to apply Ampere's circuital law.